So in this session, on this one session per whiteboard, so we come to the essential idea of quotient groups, and that is that the elements of a quotient group are the cosets of a subgroup of your group G. Okay, so you choose a subgroup H of your group G. You form the cosets of that subgroup H, and those cosets become the elements of your quotient group. Okay, that's the hypothesis. That's the main idea, right? And if that's the case, these cosets then, you have to have some kind of binary operation on two cosets, because if this quotient group is a group, it has to be closed and it has to have a binary operation. So we need to find some kind of binary operation on these cosets based on subgroup H. Okay, and the suggestion is these three lines, these essential three lines, is that the binary operation is in fact a subset multiplication. Okay, your subset multiplication is your binary operation on two cosets to form your group table of your quotient group. Right? Okay, so let's take any two members of your group. Now we've assumed you've chosen your subgroup H, so you assume you know your H. So you'll have cosets AH and BH, right? So if you're forming your group table, you have like AH, that's one element of your quotient group, and you have you have in the row up here BH, and then you have to find the entry in the group table for AH in the column and BH in the row. What is that? Now, the suggestion binary operation is to use subset multiplication. But what's the actual value? That's the problem. So now we're suggesting that these cosets are elements of a group, of your quotient group. Now, so if that quotient group is a group, you have to have closure, right? It's one of the four properties of a group. So, what does that mean? If the elements of your group are cosets, to get closure, that means the result of binary operating on two cosets gives you a member of the group, which is a coset, right? So multiplying, in a sense, so subset multiplying, two cosets has to give you a coset, right? to have closure, because we're proposing that this is a group, this group whose elements, whose members, are cosets of your subgroup H, right? So the product of these two has to be another coset, all right? So well, now we can start doing a little bit of analysis, get some clues on what that result might be. This, the resulting coset. What form might it take? Well, here's a bit of analysis. Give us some clues. The unit is a member of H. Has to be. H is a subgroup, right? All groups, subgroups, groups all have a unit, right? So E belongs to H. Therefore, A, which is AE, belongs to AH. If E belongs to H, then AE belongs to AH, right? So, and therefore A belongs to AH. And similar logic, B is just the same thing as BE, and BE belongs to BH. If E belongs to H, BE belongs to BH. Therefore, B belongs to BH, right? So, so if A belongs to this coset, and B belongs to this coset, then the product AB is a member of this because it's in the right form, right? Because A belongs to that, and B belongs to that coset, right? So AB belongs to this. So whatever this result is, some coset, because it's we have to have closure. Whatever this result is, whatever coset it is, this AB must belong to that resulting coset. Okay. Now we can go back to a theorem 46. The second part was a three-part theorem. So the second part of theorem 46, and I've put it down here to remind you. So it says if some element is a member of coset A, if your coset is A, I should be there. Got an if and only if here. So X is a member of coset A if and only if A, that's your coset, is equal to element X, H, right? Now we can use that. In fact, we're going to use this particular part of the theorem, second part of 46, a lot in next session. So keep this in mind. It is very useful. We'll use it again and again, right? Okay, so if X belongs to coset A, not if, X belongs to coset A if and only if A equals XH, all right? Now AB belongs to this, right? And this is the resulting coset. So we do subset multiplication on two cosets, and the result we get has to be a coset because this quotient group is to be a group. It must be closed. So the result of multiplying two cosets gives you a coset, right? So this coset here, call it A, right? So AB belongs to A, right? So X here would be AB. So AB belongs to A. Therefore, this coset is ABH. Right? If X belongs to coset A if and only if A equals XH. Right? Let's translate it here. Call this A. That's our coset A, the resulting coset. After multiplying these two cosets, you get a coset. Call it A. And we know that little ab is a member of big A. Right? So by using this theorem, therefore, the result here, A, is equal to X. Now what is X? Well, X is AB. So A, this thing, the result, is equal to ABH. Right? Now what is A? Well, it's the result of this. Okay? So that's big A, the coset. So that A is equal to ABH. Right? Well, there's our result. So we've used theorem 46 second part to give us this here. Right? So if you multiply two cosets, the coset that results, that you get, will be of this form. It'll be ABH. Now that's another coset, right? Because AB is a member of your original group G. A and B. If A and B belong to the group, then AB, the product, also belongs to the group. Right? So this is another coset. Maybe different from these, not necessarily. All right. So for any for any two elements of your group G, the subset multiplication. Now coset's usually just a subset, right, of these two. So it gives you this. Okay? That's very important. So if that's true, what conditions does that put on H, the subset? Right? So that's now the lead-in. So now we know what the resulting coset should be in the group table of our quotient group, where the elements of that quotient group are cosets. Cosets are based on H, your subgroup H. But for this to be true, that probably puts constraints, puts conditions on properties of H, which are what? Well, that leads into the next theorem, and you can see quite a lot of dense reasoning. And here's the statement. So now we've just found that. Right? Now that's true. And here's the statement of theorem 58. That's true if and only if x inverse hx is a subset of h. May not sound like much, but we will prove it, and the proof to here. So quite a long proof, right? So if that's true, that's true. Now it's an if and only if, so it goes both ways. And if that's true, that's true. And now we're starting to get a condition on H. And I've been saying quite a few times that you can have a factor group, a quotient group, provided that certain conditions